section, we're going to study transformation of functions. We have rigid and non-rigid transformation. Well, let me explain what we mean by rigid and non-rigid transformation. Like one of your own picture. You take a picture with your own camera, your own cell phone, and then when you look at it, and then you make it larger. As you make the picture larger, you actually don't change the shape of the picture, you just make it larger. So the basic shape of your picture remains the same. So the only thing that has changed is the size of the function. So that's one example of rigid transformation. Okay. Another kind of transformation is called non-rigid transformation. When, like, there are all kinds of programs on internet that you can download on your cell phone. You get your own picture and then use those programs to deform your face, you know, like turns your nose around, make your eyes, you know, looking weird, or your ears become longer, whatever, you know. It doesn't look like you anymore. It just becomes really funny and, you know, ridiculous looking sometimes, and funny looking. So those are examples of non-rigid transformations. Okay. So when it comes to functions, we have this similar kind of transformation, rigid and non-rigid transformation. So examples of rigid transformation for functions are vertical and horizontal shift and reflection in x-axis. These three are examples of rigid transformation that we're going to study in this class. Okay, so let's get to each one separately. Vertical shift or vertical translation is the following. Let k to be a positive real number. Let's say x equal to k equal to 5, 3, 2, whatever the number is. And then we have a graph of a function f of x given to us, and then we want to know how the graph of f of x plus k look like. So we just add that the positive real number k to the function, which is the y value. So this is actually y plus k. You see, we are adding it to y. Or we subtract k, y minus k. So if we do that, what happens to the graph of the function? In this case, the graph of the function moves up or moves down according to either plus k or minus k by k units. Okay. For example, if I have a function here, example 1, let's say this is the graph of the function f of x. So this is f of x. And then I want to know how to get the graph of f of x plus 1 from this. Okay. Or get the graph of f of x minus 1.5. So based on this explanation, what we need to do is to get this graph just like this pen. Let's say the graph is this pen, and then if I want to get f of x plus 1, just move this pen 1 unit up, like that, 1 unit up. Or if I want to have graph of f of x minus 1.5, and this pen is my graph, I just move it down 1.5 unit downward. That would be the graph I'm looking for. So this is a little bit, you know, actually artwork. Depends how good you are in drawing. So let me give it a try here. Okay. So if I want to get the graph of f of x plus 1, I have to get this graph and move it up. So what you need to do, get those important points like these points here and move those up by 1 unit. So this is 1, so this point goes here, this point goes here, and this point goes here. So something straight so I can draw the picture, and then these two, if I connect those two, you see, so this I didn't do it quite right, so it would be horizontal to this. So this straight part of the graph moves up there, and then this curvy part goes like this, you see. So this is moved up by 1 unit. Okay. Now if you want to do the other one, f of x minus 1.5. So here is 1.5. So this point goes to 1.5, goes right here. This is my green one. Here we go. Then this point goes down 1.5 units. So let's see. This point goes down 1.5. So this is 1.5 goes right here. This point goes right there. 1.5. Because each one of every 2 units is 1 unit here. And then this point goes 1.5 goes right there. So this straight line part becomes this one right here. See? And this curvy part, I don't want to call it a name yet, but this point goes 1.5 goes right there. And this point also goes 1.5 goes right there. So actually it becomes this is the graph of, so this red one is the graph of f of x plus 1, and then the green one is the graph of f of x minus 1.5. Okay, so pretty simple. As I said, just like your pen. You see, if the graph is this pen, then I add 1 unit to it, goes up 1 unit, or goes down 1.5 units. So, like those parent functions we studied at section 1.3, that's why we studied those, because we're going to use those functions as a starting function, or we call them parent functions. And then by this technique here, we're going to create new functions. For example, in this example number 2, we're going to graph the graph of function absolute value of x plus 1. As you remember, the absolute value of x function from previous section was a V-shaped graph we had. So if I graph it right here, see if I can make something, piece of straight edge, so I can draw straight lines here. Just a second, please. So I have a straight edge right here with me. So I have to make one. Okay, so this is the graph of, see, I have absolute value of x plus 1. So this is my function f of x, and I'm adding 1.5 to it. So based on this explanation, I start with the parent function absolute value of x, then I move it up 1.5 units. And I know the graph of absolute value of x from the previous section looks like this. Excuse me. Graph of absolute value, it's like a V shape. Okay. Now to get the graph of absolute value of x plus 1.5, then we have to move it up 1.5 units. It is 1.5. So this point goes to this point, and the shape stays the same. So what I would do, just draw, and of course this is 1.5 goes there. This is height 1.5 here, and then draw your V shape again, just like do it this way so it comes out, come up, just right. There we go. So this is the graph of absolute value of x plus 1.5. So maybe do this, see, let me do it again. See, this is the graph of absolute value of x from previous section is the V shape, goes through 0, 0, 1, 1, 2, 2, and so forth. And then to get the graph of absolute value of x plus 1.5, you just move it up by 1.5 units, you get this red one. So every essential point, like this point, and this point, they all go up by 1.5 units, and the shape remains the same. The next one we're going to do is square root of x minus 2. As you remember from the previous section, the square root function is a function that starts from 0, 0, goes through 0.11, goes through 0.42, the square root function, you see. By the way, let me just, before I continue this, let me just show you something here with the graphing calculator, and then I do this example. I'm going to do this one again here, because I know the function, I can do it actually on my graphing calculator, you see. So, clear this. So I put absolute value of x. Where do I get absolute x? Go to math, again go to numbers, then ABS, choose that, absolute value of x, you see. Then I go to the second line, I do absolute value of x again, math, go to numbers, absolute value of x, and then move this cursor out, plus 1.5. And I look at my window to see how it looks like. I think this is a little bit too big, so I'm going to go from minus 5 to 5, and from minus 5 to 5, make it a little bit bigger so the graph becomes bigger. So if I say graph, first it draws the absolute value of x, and then draws absolute value of x plus 1.5. So moved it up by 1 unit, 1.5 units. Okay. Let's do the same thing with square root function. Square root function, as I said, we discussed on the previous section, goes through 0.00, through 0.11, and through 0.42. So the graph actually looks like this. That's the graph of this function. Okay. And I'm going to move this down by 2 units. So every point goes down 2 units. So this is 1, 2. Let me use red. So this point becomes this. This point is above 1, so it goes 1, and 2 goes right here. This one is above 2, goes right there. So the graph actually looks like this, you see. So if this is the graph of absolute x, this is square root of x, and this is square root of x plus, minus 2. Okay. Now if I do it on the graphing calculator, I get the same thing. So go to y equal to, clear this one, both of them. So square root is right here. You see, second x squared, square root of x. And then the second one, say second square root of x. Get out of the radical sign, minus 2. So let's see what happens. My graph, this is a graph of, it's pretty much just like the one I did on the paper. Okay, so the next transformation is called horizontal shift. Vertical shift occurs when you add or subtract a number to the whole function, which is y. Now horizontal shift occurs when you add or subtract a number to the x value, because x is horizontal axis. Therefore, when you add or subtract values to that, your graph will move to the left or right. In the previous one, in horizontal shape, when you add something to the function, it goes up. When you subtract something, it goes down. But here is the other way around. When you add a value to your x value, your function, your graph of your function moves to left. You see, moves to left by 1 unit. When you subtract, it goes to the right by 2 units. Okay. So if this function is the graph, so let's read this verse and then you see, let k be a positive number. Then if you add k to x, or if you subtract k from x, the graph will get exactly the same shape, but they are shifted k unit to the left or k unit to the right, depending upon if you have plus, you go k unit to the left. If you have minus, you go k unit to the right. As I said, it's opposite of vertical shift. So how would I do this here? I want to do f of x plus 1 if this is your function f of x. So all you have to do is to look at the essential points and move those by whatever units they are, and then draw the same graph. Like this point here goes to the left, you see, because f of x minus 1 plus 1 goes to the left by unit. So this point goes here. This point moves here, and this point moves here. So let's see what the graph looks like. My homemade straight edge. So this this straight line becomes this straight line. See, and then this curvy part. Again, you see, this is a nice point, so I move to the left by 1 unit, so this point goes to this point. So you get something like this. You see? So it's moved to the left by 1 unit. So this function here is f of x plus 1. Now if you subtract 2, you go to the right by 2 units. So again, let me use the blue here. So this point goes to the right by 2 units. So here we go, 1, 2. This point goes to the right by 1 and 2. And this point goes to the right 1 and 2. And this point goes to the right 1, 2, right there. So the graph, if the straight line part remains the same, everything remains the same actually. So then like that. So this is f of x minus 2. Pretty simple. So here, the next example, we have actually the parent function. Here the parent function was a graph given to us, but here the parent function, the equations are given. See, if you didn't have this 1, then you would have absolute value of x. So the parent function is absolute value of x. See, identify the parent function. So here we parent function is absolute value of x. Here the parent function is square root of x. You see? So I draw absolute value of x just like I did before. Absolute value of x we learned from section 1.3 how it looks like. It looks like a V. absolute value of x. Okay, then absolute value of x plus 1, you see, it's the same thing, but it added 1 to x value, so it has to go to the left by 1 unit. So this point 0 goes to negative 1, this point 1 goes to this point, and this point goes right here, and the V shape stays the same. So you get this one, and this, you see, so this is absolute value of x plus 1. You can see this phenomenon on your graphing calculator very easily. See, so if I turn this on, so clear, this is math, number, absolute value of x, that's the parent function, and math, number 1. Oops, I graphed it, that's okay. Let me go back to y, math, number 1, absolute x plus 1. Okay, so I'm going to graph both of them and see what happens. Big graph. You see, it's moved to the left by 1 unit. Is exactly like what I have. Okay. Now if you want to do this guy, now the next one, you're going to do this one. Your parent function is the square root of x, as you did it for the previous example. Square root of x goes through 0.00, 1, 1, and 4, 2. Let me see if I actually get this right. Yeah. My units are a little bit different from previous example. This is 1, 2, 3, 4 is right here actually. 4. And get 2. So this is 1, 2, 3, 4. So the parent function square root of x goes through point 0, 0, 1, 1, and 4, 2. So the graph looks like that. Okay. Now if you want to move it to the right 2 units, oh boy, I don't have room here, you know. So I have to move this red curve 2 units to the right. So this point goes here, and this point goes there. So, and this point goes 1, 2. So let's see. 1, 2, 1, 2, and then yeah, it looks like that. You see, I didn't do a good job on this one. Well, not that I didn't do a good job. The units given here did not do it right. You know, I wish we had more numbers here, but I could do that. But maybe I could have used 0, 1, 2, 3, 4, 5, 6, 7, 8 instead of 1, 2, 3, 4. But the bottom line is this. This is your square root of x right there, and this is the square root of x minus 2. Has moved to the right 2 units. You see. So if I see what happens if I get the same behavior on my graphing calculator. So let's say clear, second square root of x. This is the parent function. The second square root of x and this is the square root of x minus 2, move 2 units to the right. Okay, so the same kind of behavior. Okay. The next transformation is a reflection about x-axis. Reflection about x-axis, let me just give you one situation that you see in nature, actually. See, you know, like you have mountains, you know, and then you have some tree, a lake here, a lake, and you have a tree here, and then you have the reflection of all this in the water. So you have see, like this. Something like that. You see, I'm not an artist. I wish I were, but so you have a lake here, water, and then whatever you see exactly the reflection in the water. So if I think of these mountains and everything as f of x, and then this is x-axis here, x-axis, and this is a reflection into x-axis, and I call this minus f of x. You see, so when you multiply your graph by a minus, what happens? Everything above x-axis goes below x-axis, and yet, by the way, everything below x-axis goes above x-axis. Okay, so let's see what happens in terms of function. This was, you know, like painting. So you see, this is the graph of function negative f of x is the mirror image of the graph of f of x with respect to x-axis. So like here, if you want to know if this is f of x, then you want to know what minus f of x look like. So to get minus f of x, basically what you have to do physically is to fold your paper along along x-axis like this. See, if this is x-axis, and then if I have a, let's see, if I have something like this, then if you want to get the reflection, then you fold your paper along x-axis like this, and then if it's a pencil, you know, let me see, make a pencil. See, I have a pencil here. You see, if I had pencil here, so it would give a mark. See, if this is your f of x and this is x-axis, then you fold your paper along x-axis, and then you kind of rub behind your paper like this in the hope that you get some mark. You see, I got some mark. You see it here? You see? This is, if this is f of x, this is minus f of x. See, that's what. So basically, what happens? Everything above x-axis falls below x-axis. Everything below x-axis goes above x-axis. So this point goes from negative 2 goes to 2, and this point 2 here goes to negative 2. So this straight line becomes. This is straight line, and then this one goes like that. So this is minus f of x. Okay. Then now if you actually have functions like cube root of negative cube root of x, then how would I do that? Well, first we have to see what the parent function is. The parent function, in this case, I don't have room here. I wish I had more room. So I have square root of cube root of x. And the previous section we learned how the graph of cube root of x look like. See, if I do it on my graphing calculator, actually, cube root, you see, you have to get go to math. See, cube root is right here. Cube root, so number 4. So cube root of x. So if you look at that graph, my window is not really. Let me fix my window, make it more symmetric. So from minus, say minus 10. And then I go from minus 3 to 3, make it bigger. See, this is the graph of cube root of x. Goes through point 0, 0. Goes through point 1, 1. Goes through point negative 1, negative 1, so it looks like this function, so it looks like I kind of did an okay job. Okay, so this is your parent function, cube root of x. Now if you want to do negative cube root of x, then you have to reflect that. So let me do it with the graphing calculator, but of course new graphing calculator, if any of you have, when you do more than one graph, then the different graphs have different colors, and that's nice. But this is an older version, and I don't have the luxury of having different colors for my different graphs. So if I go ahead and say negative cube root of x, and then say graph, you see, this part below goes above and this part above goes below. See, so I get something like, this part falls below and this one goes above. This is minus cube root of x. Okay. And the next example kind of has two operations involved here. You see, your parent function is x squared. You see, so I start with x squared, and we learned what that x squared is from previous section. Is a shape. We call it a parabola, but I hate to use that terminology because we haven't really studied that yet. But we have a parabola here. This is a graph of x squared. That's the parent function. There are two operations involved here. One is that I multiply it by a negative. When I multiply it by negative, it just flips down under the, I'm going to use the pencil here. See, so it becomes like this. So this is negative x squared, the first one, and then you add to negative x squared. Now negative x squared is your parent function, and then you subtract 2, so you move it down 2 units. So this point goes 1, 2, and it becomes like this. See, minus x squared minus 2. You see, so I moved it down. So 2 operations. The next one is also interesting. It has 3 operations actually. You see, first you start with x squared. That's your parent function, which is right here. Okay. Then the first thing you do, you subtract 2 from x, that causes this graph to move to the right by 2 units. So I move this to the right by 2 units. So I'm going to use the pencil. So 1, 2, like that. So this is x minus 2 squared, moved to the right 2 units, you see. Then you multiply it by a minus, so this pencil drawn graphs is going to flip downstairs, so it's going to look like actually I didn't do that right, but that's okay. Falls down like that. This is minus x minus 2 squared, and then finally I subtract 1. I move this guy 1 unit down, so this is 1 unit, so this one goes here, so it goes like this is the final one. So this is minus x minus 2 squared minus 1. So let me explain this one more time. You start with your parent function x squared. The first operation is that you move it to the right by 2 units. So you get this, and then you multiply it by a negative. You flip it downward. You get this. And then you subtract 1 from the whole thing, so they move it downward, or vertically shift it downward by 1 unit. So that's the final product here. Okay. And these are the only rigid transformations we're going to study for this course. And there are a few other ones that we don't do, but there are also non-rigid transformation. As I said before, we're not going to do any examples of that beyond the scope of this class. So this type of transformation cause distortion in the graph of the function. Examples of such transformation are vertical and horizontal expansion. For example, when you multiply a function by a number, for example, if I say 2 times f of x, if I do something like that, you see, 2 times f of x, then in this case the graph becomes sharper, you know, you just stretch it upward. Or maybe if I say 1/3 f of x, if you multiply by 1/3, then you kind of flatten your graph a little bit. So vertical or vertical squeezing, okay. So, but we won't do that because the shape changes, and really we don't see any point of discussing this. So this concludes this section. We're going to do next section shortly.